Welcome to NPTEL 2 video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 24, this module 5 and lecture 24, geosynthetics in pavement. I will now focus recap of previous lecture, this is design problem, design of reinforced unpaved road, that is Giroud and Hand 2004, design method for flexible pavement, that is ASTO 1993. In this lecture, I will show you that some Excel program, how you can calculate the design of unpaved road without and with geosynthetics with 3 procedure. Procedure 1 is IRC 372001, that is only without geosynthetic material, and procedure 2, that is Giroud and Hand 2004, without and with geosynthetics material, and procedure 3, that ASTO 1993 design method for flexible pavement without and with geosynthetics. First of all, I want to show that IRC 37201 method, that is determination of the cumulative number for standard axial load, that we use this equation A is equal to P 1 plus R to the power x into D, and Ns is equal to 365 A 1 R to the power n minus 1 by R into F. So, here we want to calculate what is the A, and also we want to calculate what will be the Ns. Now, for A we require P, R, X and D. So, here it is given that P is equal to 1000 value and number of years, that is 5 here, and the annual growth rate is about 10%, and time distribution factor for two-way road, which we should calculate, and also initial traffic volume of the construction period A we have to find out, and also we have to calculate the what will be the design life of the pavement after completion of 15 years, and then you have to calculate this physical damage factor F. So, first of all, that we want to calculate that lane distribution factor. So, lane distribution factor, we have considered that 2-lane single carrying road and lane distribution factor in terms of the percentage of the total number of the commercial vehicle in both direction is about 75%, and that is why this is 75%, that means D is 75%. Now, you have to calculate vehicle damage factor, that is F. This F can be choose from this table. That means we know that what will be the initial traffic volume in terms of number of commercial vehicle per day. We are assuming the number of commercial vehicle per day 150 to 1500, and we are considering the terrain, whether it is a plain or hilly, we have considered the plain terrain, and that is why this vehicle damage factor is 3.5. So, you know the vehicle damage factor, that is 3.5. So, we can see here that vehicle damage factor F is equal to 3.5. So, we know here F is equal to 3.5, and we know here D is equal to 75%, and R etc. everything is given. So, we can calculate A, we can calculate N of S. So now you calculate that NS value. So here is shown that NS value. So from the output you can see that NS value is 449.03. So we are having this, all the values are known, NS value is 49.03. And from this you can calculate the what will be the total payment thickness, that will be 924 for the California bearing ratio value is 2. So NS, you know the cumulative number of standard axial load. So this is the design chart. This is for design chart for pavement thickness as per ISC 372011. There are two charts has been shown. One is for the design traffic is 1 to 10 MSA. This is the relationship between the what will be the design traffic and what will be the thickness of the pavement for different MSA. And the right hand side is given for 10 to 150 MSA. So here as our NS value is 49.03, so here you can see this is 49.03, so we know that what is the NS value, and then we move up, and then this is the CBR value is equal to 2, this is CBR value is equal to 2. So for this 49.03 NS value, you move up and then CBR is equal to 2, and then you move horizontal, and then you can calculate what will be the thickness of the pavement. This will give 924. So this will give the value of 924. So you can calculate this 924 millimeter of total pavement thickness. This is IRC code specification without geosynthetic material. Next, procedure 2, that Giroud and Norrie 2004 without and with geosynthetic material. Here you have to determine the thickness for unpaved road without and with geosynthetics. We use this equation, R is equal to root over P by pi into P, and PH0 is unladen force. We use this equation, and C is equal to this. So here that axial load, here we use this equation, and here the axial load is given 135. So wheel load is kilonewton P, half of this axial load, that is 67.5, and the tar pressure is given, kPa is 500 kPa, subgate CBR percentage is given 2, allowable rod depth is millimeter is 40, then factor Fs is 30, factor Fc is equal to 75. So for unladen force, bearing capacity factor is 3.15. So you have to calculate that what will be the unladen force bearing capacity of subgrade soil. So you can see that here the output data, the radius of equivalent contact R is equal to 0.207, unladen cohesion of subgrade C is 60. So allowable bearing capacity of subgrade soil without reinforcement 13.56. So this is less than the wheel load 67.5 kilonewton. As the pH unladen force is less than the wheel load, a base course without and with geosynthetics is required. You can see here that how this is less than 67.5 kilonewton. This is the 67 wheel load, 67.5 kilonewton. So for it is less than the 67.5 kilonewton. Therefore, it is required to introduction of the geosynthetic material for the pavement design. Next, design base course without and with geosynthetics. So this is the equation we will use for this design, and here base course CBR is 20, CBR of the subgrade soil is 2, allowable rod depth is 40 millimeter, this is factor FC is 30, factor FP in kilopascal is 75, and geogrid aperture stability modulus, this is very important, that is 0.65, number of the axial passes N is equal to 1000, wheel load P is equal to 67.5, and we consider bearing capacity factor for unreinforced unpaved road, that is 3.14, bearing capacity factor for geogrid reinforced unpaved road, that is 5.71, and bearing capacity factor for geotextile reinforced unpaved road, that is 5.14. So, then we can now calculate, and here you can see that determination of thickness without and with geosynthetic material, this program has developed, and then it has you can see that how by the iteration, this is how the minimized value has come. After that you can almost finish here. So, you can get that initial for the modulus or modular ratio, bearing capacity factor, you can see 0.3 and then 0.5, then 0.63, it is stabilized. So, for unreinforced case, thickness of the pavement is about 0.63 meter, but if you use the geogrid material, you can see it is finished at about 0.2 meter. So, what will be the assumed base course thickness is equal to required base course thickness. Okay. This is for geogrid, the thickness of the pavement will be the 0.20 meter. Similarly, that if you use the geotextile material and assume base course thickness, okay, and then ultimately you are having 0.43, and then which is matching with the required base thickness 0.43. Now, all the three procedure have been shown here for without geosynthetic material, with geogrid material, and with geotextile material, and now you can look that what will be the saving. So, base course thickness for unreinforced unpaved road is 0.63 meter, and base course thickness with geogrid material 0.2 meter, and base course thickness with geotextile is 0.48 meter. So, percentage of saving in case of geogrid is about 68.254, whereas percentage of saving in geotextile is 31.746. So, we can see that how that geosynthetics can help to reduce the thickness of the pavement. Now, we will address that procedure 3, that is ASTO design method for the flexible pavement without and with geosynthetic material. Now, here that is surface course, base course, this is sub base course, and this is the subgrade, and here expected tandem 30 kips, and number of the annual growth rate per year is 1 lakh, axial load equivalent factor 1.38, director different factor DD, you know what is that length distribution factor, and you have to calculate that reliability factor. So, this is reliability factor is 95%, which you can obtain from this chart. It is a level of reliability, R for the design is 95%, and correspondingly you can also determine what will be the value of ZR value. So, ZR value, this is the reliability, so this is the reliability value, okay, and this is the ZR value. Here reliability is 95%, So, corresponding ZR value is minus 1.645. So, you are getting minus 1.645. So, here this reliability value is having minus 1.645 for the reliability level of 95%, and H0 etc. are given, and from there you can calculate the reliability factor. And next, that you have to select the value of M value. You can select the M value from here, because we have considered DN is good and it is for 1 day, and this recommended value of M value, that is good, and then also it depends upon the moisture content, and you are considering that what should be the M2 and M3 value. And here, because in base and subbase course is the same material, so this drainage coefficient M2 and the M3 we kept the same, that is 1. That is why drainage coefficient M2 is equal to 1 and drainage coefficient M3 is equal to 1. This one is for the base course, another is for the subbase course. So you can calculate that what will be the value of M. So next you can calculate the determination of W18. So this is the W18 is expected traffic per year into axial load equivalent factor into traffic growth factor into DD into DL into FR. So from this you can calculate W18, which is coming 5.8 MSA, that is million standard axial. Now determination of SN by the trial and error method. So you can determine the SN value by trial and error method. So you can obtain that structural number about 6.160. So you can go by the trial and error, you can see that you have got that this is log W18 is 6.67, and by the trial and error, you can have the structural number value is equal to 6.160. So you have used this equation, the right hand side, this equation, you know all the value on the left and the right, and then you can calculate that what should be the structural number, that is 6.1. So you can calculate this structural number knowing that W of 18, or you can use also the design chart. So this also you can use design chart. There are two design chart. One is for 1 to 10 MSA, another is 10 to 150 MSA. So you can determine the structural number, use this design chart. So this design chart show the relationship between the CBR and the structural number SN for the different MSA 1 to 10 MSA. Here, because this CBR value is 2 and the structural number value lies between 6 to 8 nearer here. So you know the CBR move up, and then you check the structural this MSA value, this is about 6 point something 16, and then you move the horizontally, then you can calculate that what will be the structural number. So that you can calculate the structural number knowing the value of this, what will be the load, this 5.8 about MSA. So this is for 1 to 10 MSA. You can also calculate for this 10 to 150 MSA. When you use from 10 to 150 MSA for defined value of CBR and the structural number. If it is a more than 10 to 150, so you can adopt this chart. And this is the for design, for surface layer course you have taken A1 and the base course and the sub base course, and you assume the surface layer depth is equal to 0.21 and assume the base course D2 is 0.25 and sub base course D3 is equal to 0.468449. So total thickness you can also obtain 0.9284 meter. So this is in case of the unreinforced, what will be the thickness of the pavement considering all the structural layer coefficient from this equation. Sn is equal to A1 D1 A2 D2 M2 plus A2 D3 M3. So you can determine the structural number and you can determine what will be the thickness of the pavement. Now if you move for the reinforcement case, where you have to consider in this equation that Sn is equal to A1 D1 plus LCR. LCR is equal to linear coefficient ratio into A2 into D2 into M2 plus A3 into D3 into M3. So if you know that what is the LCR, so you can calculate that also structural number. And this LCR you can calculate from this curve. So this is the curve which shows that CBR versus layer coefficient ratio LCR for a geosynthetic material which is a geocomposite material which has a geogrid and non-woven geotextile and tensile strength is 40 kilonewton per meter. So knowing the value of CBR you can calculate the what will be the value of LCR. So here the layer coefficient ratio LCR value is equal to 1.4. So you can substitute this value, that is LCR. So from this figure you can calculate that what will be the LCR value. If LCR value is equal to 1.4, then you substitute this value in this equation 1.4 and then you can calculate that what should be the thickness of the pavement. So here the surface level course D2 is equal to 0.21, D1, D2 is equal to 0.25 and sub base course D3 is equal to 0.33 meter. So total thickness is 0.79 meter. So then you can see that what will be the percentage of saving. So saving in the sub base course about 28.57%. So without and with geosynthetic material you have obtained that how you are saving this thickness of the pavement. So you can use this Excel program for the determination of the thickness of the unpaved road without and with geosynthetic material. So next, development of design method for geosynthetic reinforced flexible airfill pavement. So Barenberg design method, Barenberg detail 1975, he has given that sigma z is equal to NC into Cu. What sigma z is allowable stress on the subgrade, Cu is equal to Undine cohesion and NC is equal to bearing capacity factor, that is 3.3 without geotextile and NC is equal to 6.0 with geotextile material. This is they have performed the field test and from that field test they obtain this value. Now Federal Aviation Administration FAA design method, the thickness of the different component of the pavement are determined based on the California bearing ratio CBR values using the following equation, that is T is equal to alpha into root of A into 17.9 into P by CBR minus 1 by pi. This is other and Whiskers 1975. What T is equal to thickness of the aggregate layer centimeter, A contact area of one tire that is centimeter square, CBR California bearing ratio in percentage, PE tire pressure of a single wheel load, that SWL, or equivalent single wheel load ESWL, or that is equal to SWL but single wheel load divided by contact area of one tire, or equivalent single wheel load divided by A, that is contact area. And alpha is the load repetition factor depending on the number of the load repetition and carriage configuration. So, some modification has been made. This is number of the coverage corresponding to 25,000 annual departure of an aircraft on a pavement having 20 years of design life exceed the maximum value of coverage, that is equal to 1 into 10 to the power 5 available in the chart provided in the Acrodome Design Manual Part 3 Pavement 1983 for evaluation of load repetition factor alpha. Hence, this original charge is extrapolated to include up to 3 into 10 to the power 5 coverage as shown in the figure. Because nowadays that because for aircraft weight are increasing, so this is required for more. So, initially that whatever it was there, that is 1 into 10 to the power 5, and this charge has been extrapolated and include up to, you can see that which was 1 and it was up to 3 into 10 to the power 5, it has been extrapolated, because for heavy Boeing etc. where there would be heavy load. So, this is the modified load repetition factor, that is alpha, versus the coverage, this design life for 20 years from the Aerodrome Design Manual Part 3 Pavement. So, this design chart has been modified and we will use for our design. Now, pass to coverage ratio is the ratio of number of the annual departure to the equivalent number of the departure. Now, this table 8 pass to coverage ratio for flexible airfield pavement, that is Aerodrome Design Manual ICAO Part 3 Pavement 2nd edition 1983. Here for the different types of the aircraft, you can see the single wheel, dual tandem, B747, Boeing DC 1010, DC 10 to 30, L1011, and this is to pass to coverage ratio. So, this starting from 5.18 to 1.81. So, we will consider some cases for design that Boeing 747 which pass to coverage ratio will take 1.85. So, as for example, if the annual departure in passes is 1200 for B747 type aircraft, the number of the landing wheel is 8. So, pass to coverage ratio as obtained from this earlier table is 1.85. This is pass to coverage ratio 1.85. So, coverage will be 1200 because number of passes 1200 divided by that what is the pass to coverage ratio is 1.85 and this for the 20 years. So, this will give you the 12972.97 for 20 years design life. So, knowing the coverage 12972.97 load repetition factor alpha determined from the modified chart, that is alpha is equal to 0.75. I will show you that here this is the coverage and this is the load repetition factor, that means alpha, and these are the number of the wheel used. It may be 1, 2, 4, 6, 8, 12 and 24 number of the wheel is used. In this our problem we are assuming that number of wheel is equal to 8 and we know that what should be the coverage, that is about 12,972. So, it is somewhere here that coverage is 12,972.97 and then we know the coverage value and we know that what will be the number of the wheel. So, number of the wheel is equal to 8. So, here number of the wheel is equal to 8. So, knowing the coverage we know number of the wheel. Then he moved horizontally and to the load repetition factor alpha. So, this will give you the load repetition factor alpha. So, this alpha value which lies between 0.7 to 0.8. So, this will give you about alpha value is equal to, that is 0.75. So, you can calculate from this design chart what will be the load repetition factor, that is alpha. So, we can calculate the load repetition factor. Next to, in the original FAA design method, it was assumed that 95% of gross weight of the aircraft is taken by the main landing gear. However, in the present study, it is assumed that 100 to 135% of the gross weight of the aircraft is taken by the main landing gear. For single wheel gear aircraft, no such special assumption is needed. So, this is the percentage of gross weight of the aircraft taken by the main landing gear of various aircraft. This is the modified method. You can see here type of the aircraft: dual wheel gear, dual tandem wheel gear, DC 1010, 10CF, A300, B2, B4, B747-100, SR 200 BCF and B747 SP. For this, we assume the percentage of the gross weight carrier by the main landing, it starts from 100 to, you can see we can go up to 135. So, this is what it has been modified, and because for the heavy load you have to consider the landing gear is more. For B747-100 SR 200 BCF, assume the percentage of gross weight carried by the main landing gear is 135%. So, gross weight of the aircraft is 385560 kg is given. So, carried weight by the main landing gear will be 385560 into 1.35, that is 520506 kg. So, number of the wheel is 8. So, ESWL will be the 520506 divided by 8 is equal to 65063.25 kg. And you know the contact area capital A is equal to 1580 into 64 centimeter square. So, tire pressure PE is equal to ESWL divided by A, that is 65063.25 divided by 1580.64, that is 41.16 kg per centimeter square. So, thickness can be determined from this following equation, that is T is equal to alpha root over A into 17.9 PE divided by CBR minus 1.5. You know that what is alpha value. If alpha value is known to you 0.75, you know that what will be the contact area A which is given, you know that what will be the PE value, and you know that what will be the CBR value, then you can also calculate what will be the thickness of the pavement. Now, combination of Barenberg design method and the modified FAA method. In this method, the thickness of the aggregate layer for various CBR value is determined using the design evaluation given by Yoder and Whiskey 1975, considering all the modification. The CBR value can be converted into corresponding Arnden cohesion value. That means Cu is equal to 30 into CBR, where Cu is equal to Arnden cohesion value in kilopascal. If the bearing capacity is provided, we can easily determine the CBR values using the above relation and mention Barenberg equation. The appropriate bearing capacity factor NC has to be considered for reinforced, that is 6.0, and unreinforced case it is 3.3. And this is the table, different types of the aircraft, gross weight and number of the annual departure. This is the, you can see the different types of the aircraft is given, okay, and this is the gross weight also it is given, which lies between 13,600 to 34,000 kg. Even then you can have 1,42,000 to 1,57,000 of kg gross weight, and the number of annual departure also nowadays it is 1,200 to 25,000. This is the number of annual departure, and gross weight you can see how it is the increasing. So that is why the design chart, modified design chart will be very useful. So design chart are prepared for different types of the aircraft, gross weight, number of the annual departure, and x axis represent the CBR value and y axis represent the thickness of the value. For unenforced case, the thickness will directly be obtained from the design chart. For the reinforced case, the thickness will be corresponding to the CBR value 2 times that of the unenforced case. As for example, the thickness has to be determined at a CBR is equal to 2. For unenforced case, one will use the design chart directly. However, for the reinforced case, and we have to find out the thickness at CBR is equal to 4 from the same design chart. Here you can see that design chart, this is for flexible pavement design curve for the critical areas, that is B74700 and SR 200 BCF for gross weight of 385,560 kg, and this is the annual of departure, and this is the thickness of the pavement. So if you know that what will be the annual departure, and if you know the CBR value in unenforced case, let us say consider the unenforced case that CBR value is 2, and the annual departure if you know, then you can calculate what will be the thickness of the pavement in unenforced case. When it is the reinforcement case, this it will be the 2 times, that means 2 will be the 4, and then you know that what will be the departure D1 or D2, D3, D4, D5, and then correspondingly you can also calculate that what will be the thickness of the pavement with geocentric material. I am showing that how you can use this chart. Let us say this is the unenforced case. And given CBR value is equal to 2, an annual departure let us say annual departure D1 is equal to 25,000. So from this design chart, knowing the value of CBR, if CBR value is equal to 2 and annual departure let us say is equal to 25,000, so you can calculate that what will be the thickness. This thickness will be about your 300, this will be about 300 centimeter. So this thickness will be about 300 centimeter. So thickness of the pavement will be 300 centimeter. Okay. But in case of reinforced, case, so this CBR will be the double, 2 into 2, that means CBR will be the 4. Let us say annual departure D1 also equal to same, that is 25,000. So you can calculate the thickness from this design chart, so that will give you about 210 centimeter. This thickness will give 210 centimeter. So you can have, when it is the 4, then you can D, and then you can calculate the thickness about 210. So that means that you are reduction of the thickness due to the introduction of the geosynthetic material about 30%. So this design chart can be used. So this unenforced and reinforced aggregate thickness and percentage saving in aggregate for B74700 SR 200 BC and F aircraft to a departure of 1200. Here you can see the gross weight, different gross weight is given, and when CBR value is equal to 1, what will be the thickness for unreinforced case, what will be the thickness for the reinforced case, and you can see percentage of reduction about 28.5 to 29 or 30% is saving. When the CBR value 2, here it is the thickness for pavement for unreinforced case, and thickness for the reinforced case is 106 to 162. You can see in all cases the thickness of the pavement is reducing due to introduction of geosynthetic material. So, percentage of reduction also is vary from 31 to 32 percentage. When the CBR value is 3, unreinforced case thickness of the pavement lies between 124 to 190, but in case of the reinforcement, thickness of the pavement lies between 84 to 132. So, reduction of the thickness is coming about 30 to 32 percentage. Now, pavement overlay. When the crack occur over the pavement overlay, that is asphalt overlay, water can percolate through it, causing the rapid deterioration of the highway or roadway. You can see that road where there is a pothole, there is a reflection cracking in some of the highway of India. You can see this is a maybe longitudinal cracking, sometimes you can see also the alligator cracking and different types of the pothole. So, here we wanted to address that how the geosynthetics can help to retardate the cracking and what kind of the geosynthetic material we should adopt. Now, you can see mode of crack propagation after Enkler and Bonner 1997. You can see that due to the temperature sun. So, there is a movement of in a crack due to the thermal variation. So, there is a development of thermal stress, and this is expansion and contraction. So, here you see that how the movement in crack due to the thermal variation or due to the rain, when there is a rain or there will be the moisture stress. So, you can see that movement in a crack due to the moisture variation. So, first of all you have to think that the cause for the mode of the crack and how it propagate. It may propagate due to the temperature, it may propagate due to the moisture or rain, and also there is a possibility for any soiling, then there is a possibility for cracking. So, the crack may occur due to the thermal stress, also it may occur due to the moisture state, because there is a variation of the moisture variation and thermal variation. Also that when the opening and vertical, you can see opening and there is also vertical shearing of crack. So, when the traffic move, it goes down, it goes up, so there is a formation of the shear and it open. So, also the crack also form. Also traffic induced horizontal shear of a crack, and this is braking and the acceleration of a heavy vehicle. When there is a brake or acceleration of accelerating of a heavy vehicle, then there is a possibility for the traffic induced horizontal shear of a crack will form. So, you can see that how it is the shear due to the braking or accelerating of the heavy vehicle. Now, traffic induced, that is shear at a crack end, it is like a seizure. So, this is the crack at the surface and this is shear. So, when the heavy vehicle move, you can see there is a possibility for the shear and there will be the crack at the surface. So, traffic induced scissors here at the crack end. So, you have observed the different types of the cracking pattern. Now, geosynthetics for pavement overlay. So, it is a conventional to maintain the road year after year. Therefore, a water barrier layer is needed to protect the pavement from degradation due to ingress of water. What we do? We generally clean, fill and resurface the pavement with bituminous layer, that is asphaltic cement of thickness ranging from 25 millimeter to 100 millimeter as an overlay on the existing pavement. However, it is observed that reflection crack occur from the old pavement into and through the new overlay. So, geosynthetics can be used as a superior moisture barrier as well as retardating the reflection crack in the pavement. Now, you can see that how the impregnated non-woven geotextile with the proper coating with the asphalt has been used. So, if there is a formation of the crack, you can first of all to clean this and fill up with the coating material, and then you can place the non-woven geotextile material, and then top of the non-woven geotextile material you can provide with the asphalt, because the non-woven geotextile material there is a opening size or apparent opening size of the non-woven geotextile material, and it should be filled coating with the asphalt. Then this non-woven geotextile material will act as a barrier. So, crack will not propagate on the surface of the road. This crack can be prevented by the introduction of the geosynthetic material. So, here you can see that this is the granular base, this is the old pavement and this is the new pavement, and then there is a old pavement crack has formed, and you can see the how the reflection cracking occur without the geosynthetic material, and right hand side you can see that what the geosynthetic material has been introduced, and this is the old pavement and tack coat saturated geotextile here. So, when the crack will form, it will propagate on the top and then diverted on this direction. So, it is arrested, the crack will arrested, it will not appear on the top of the surface. So, this is the new overlay and this is the old overlay. So, use of geosynthetic material can prevent the reflection cracking in the pavement. It can be used beneath the overlay to reduce the crack propagation along its length. It can also increase the stiffness and load bearing capacity of the asphalt concrete pavement. So, this is one kind of the asphalt reinforced geogrid. It is a geogrid material and also laminated with the geotextile material, and this is the asphalt coated. So, you sometimes do not need to provide with the asphalt overlay on the top, it is also available in the market. So, type of geosynthetics for pavement overlay. Standard asphalt or polymer modified bituminous layer are used as overlay of pavement. Different types of geosynthetics available for asphalt overlay are non-woven geosynthetics material, that may be the synthetics or natural, or woven geosynthetics material, that may be synthetics or natural, asphalt reinforced geogrid or geogrid, it may be made of polyester or high density polyethylene, etc. Geocomposite material, where you can use the geogrid and combination of the geogrid and the geotextile material, whether it is a woven geotextile or non-woven geotextile material. Also the glass grid and polypropylene material, nylon, jute and coir. So, main function of the geosynthetics, it acts as a reinforcement function and also the water barrier, cushion, separation and filtration. The use of proper geosynthetics will be helpful for the retardation of reflection cracking. It will reduce the maintenance cost as well as increase the roadway life. It will also increase the serviceability of the pavement overlay. Brown, Roddick and the Hughes 1984 reported that geogrid is good to minimize rutting. Type of geogrid play a very important role. Polypropylene or polyethylene will not properly bond together with the asphalt. So, bituminous coated flexible geogrid ensure good bonding. Geogrid shrink on hot asphalt for molecular stress relaxation and loss of strength. Even then, geogrid act as good crack arrestor for prevention of reflection cracking in pavement. Bituminous coated glass grid has high tensile strength and high modulus, low creep and low elongation. So, it can be used for rehabilitation or retardation of reflective cracks in an existing pavement. Track coat, the exact quality of the track coat is reported by Walton et al. 1982. It is very important that what quantity of track coat you should use for your design. So, here Walton giving the equation QA is equal to 0.36 plus QS plus minus QC. What QEF is the required amount of bituminous track coat, that is liter per meter square. QS is your required amount of bitumen for saturation of geotextile liter per meter square, and C is adjustment factor based on the sealant required for the existing condition of the surface layer, that is liter per meter square. So, it is very important that what amount of bituminous or track coat is required. The geotextile is saturated with bitumen at 120 degree centigrade for 2 minutes. Walton et al. 1982 reported that value of QA varies from 0.09 to 0.59 based on the surface condition of the pavement. So, it depends upon the surface condition. Construction of overlay. The ground surface must be free from all kind of debris, rot, dust, etc. Crack should be filled with hot mix and asphalt. Then track coat is needed to spread over the entire surface of the existing pavement. Then geotextile should be placed in order that there should not be any wrinkle or the fold. So, you can use, if this is the existing road and this you can see there is a formation of the crack, and then this crack is to be filled up with the hot mix. It should be clean, thoroughly clean it, and then you fill up with the asphalt. Okay, it should fill up with the hot mix or the asphalt, and track coat is needed to spread over the entire surface here, and then you should place this geotextile material on the top of this. Okay. So, this is the geotextile material, it may be geogrid or geotextile material here to place, in order that there should not be any wrinkle or the fold on this. Now, care should be taken so that there should not be any damage of the geotextile material due to the movement of the any track on the pavement surface, and sometimes you can overlap the geotextile material. It should be between 12 centimeter and 18 centimeter, and one has to be careful about the temperature. The temperature of bitumen should not exceed 135 degree centigrade to 150 degree centigrade. So, after proper curing, so you can provide with the asphalt on the top of this. After proper curing, then the traffic should be open. So, if you do the proper kind of the placement of the geosynthesis material and proper selection of the geosynthesis material, then you can retardate the cracking. With this I ended up this today's lecture. If any question, thank you.